So I'm gonna try to summarize what I have been up to in the last 2 years on the topic of robustness and neural network learning. So this is joint work with a bunch of people, visitors and mostly interns at Microsoft Research. So Ronan Eldan, with now at the Weizmann Institute, Yintat Lee, Yuan Julie, Dan Mikulincer, Mark Sellke, and Dheeraj Nagaraj. They were all my interns over the past few years. And I will primarily talk about a recent paper with Mark Sellke. So I will explain the whole context. And I think the upshot is that we maybe finally understood something about the importance of scale in neural network learning. So I will try to explain that. So this is based on those 3 papers. This one with Ronan, Yintat, and Dan, which appeared at NeurIPS last year on network size and size of the weights. This paper from Court this year with Yuan Julie and Dheeraj Nagaraj on a law of robustness for 2 layers neural network. And again, this more recent work, which shows that the law of robustness is actually completely universal in several senses. So I will explain that. But let me start with the context of this work. So the context of this work is really this plot from OpenAI. On the x-axis, you have years or decades. And on the y-axis, size of the models, or in fact, amount of computation in this case. And you see that there is a breaking point, like, a decade ago, where something really dramatic happened. And suddenly we started to scale things up like crazy, and things were working better and better. So this is this observation that, I think against all odds, against all of our prior knowledge, bigger just seems to be better. So bigger models perform better, they learn more things, and we want to understand why. Why is that? It's not at all in accordance with what we were understanding before. So to set the expectations, I'm not gonna answer this question. This is a very, very difficult question, but I think we uncovered one part of the story, namely that actually bigger is necessary. Okay, so I won't tell you that it's sufficient. Okay, so don't get your hopes too high up. I don't know that it's sufficient, but I will show that it is actually necessary. And to fix ideas, I would like to first do a very small and quick exercise of getting some of the numbers in your head, like the scale. I think many of you already know those numbers, but for those of you who don't, it's really useful to go through this exercise. So MNIST data is the most famous and the historic data set for machine learning. It's 60K data points, and these are these 28 by 28 resolution images of digits. And what's happening nowadays is that we're training models with millions of parameters. Okay, so you're training huge, actually big neural network, even on MNIST. And you really, as you train bigger and bigger network, things get better and better in several respects. And really the question is, how does this make sense? Where is the information in the MNIST data set? You only have 60K data point. How is it that with 1 million parameter, you do better than with 100K parameter? At some level, it doesn't make sense. From classical, learning theory, it doesn't make sense. Like the generalization bound should be square root of the number of parameters over number of data sets. So if number of parameters is larger than number of data sets, what is happening? We don't really understand. Don't worry. Next slide, I think, is a benign overfitting slide. That many of you know and are probably anxious for me to talk about. So this is coming up. Let me just give you some other number. ImageNet, this is 1.4 million images, which are bigger images. There are 3 channels, and they are 256 by 256 in size, in resolution, and models of hundreds of millions of parameters. So again, more than 2 orders of magnitude bigger than the number of data points. In NLP, we're talking about billion, tokens, and models with hundreds of billions of parameters. So we really want to understand this. Now, there is a very nice series that has been emerging over the last couple of years, which is called Benign overfitting, and it goes like this. So here is an experiment from a very nice paper of Nakuran et al. From 2 years ago on CIFAR10, so yet another data set, where they add label noise. Okay, so keep that in mind. It's important. They add 15% of label noise. And what they plot is size of the model versus the test errors that you can get. And classical learning theory would tell you that first you drop, as you fit better and better, and your generalization is good, and then you start overfitting. Okay, your test error goes up. And this is exactly what they observe, except that now there is this double descent. There is this, second descent phenomenon where as you make it bigger, it goes down again. Okay, and it goes down both to the level of the best under-parameterized model, but in fact, it even goes a little bit below. Okay, and never mind like this shading of the number of epochs. You can just think that we're running, you know, the full thing, so it's really the black curve that matters. And also note the early stopping curve. If you did stop your training earlier, then you never overfit, in fact. Okay, so remember the label noise and the early stopping. These are things, maybe I won't mention them again, but you should keep them in mind. These are important parameters of these experiments. So from a theory perspective, we are starting to understand what happens, at least for the case of linear models. So I'm citing a couple of papers here. I think some of those papers are in the audience. And really the upshot is that more parameters certainly does not necessarily hurt. That's the first thing. And in fact, sometimes it can help a little bit. You can even get a little bit below, you know, what you would get with the underparameterized model. Now, what I'm after is something really entirely different. What I would like to show is that scale does not, you know, help a little bit or, you know, allows you to recover what early stopping would do or something like that. I would like to find a mathematical framework where I can say that scale enables a completely different behavior, like something that was just completely impossible with smaller models. Okay, so this is my goal, to try to develop a mathematical series that supports this claim. And I would say that double descent is not about that. Also, you know, maybe technically, the benefit that you can get in double descent is by linearly scaling the number of parameters with the training set, with the training data set size. Whereas what I'm after is really trying to get an order of magnitude, like several order of magnitudes bigger, like that it's not about n, it's about some other parameters. It's not about the number of training points. Okay. And so I would say these double descent experiments don't show this entirely new phenomenon. But there is another experiment that I have known for several years, which actually shows a real jump, a real phase shift as you increase the model. And this is the experiment from Madri et al. From 2018, and which is actually well known in the robustness world. So what they did is, here is a picture, very simple, on MNIST. Again, on the x-axis, you have the size of the model. On the y-axis, you have the test error. There are 3 different colors. It doesn't really matter what those 3 colors are for the sake of this talk. But the point is that you see a phase shift. Suddenly, something like dramatic happens as you make the network big enough. And capacity scale 4 is already, I think, it's already 1 million parameters. Okay, so it's exactly what I was talking on the first slide. Like at 1 million parameters, something new happens on MNIST. So the way these models were trained was actually by doing adversarial training. So you're trying to make the model not only fit the data, but to fit it robustly. And basically it fails. It just, does not work when the model is too small. And then suddenly if the network is big enough, and big enough is, many, many times bigger than the size of the data set, then it starts working. And the different shades are just, how you test adversarial robustness, whether you test this, like what kind of adversary you test again, whether it's one-step gradient descent, multi-step gradient descent, we have some understanding of what that means theoretically. If you want, you can ask me a question about this. It doesn't matter for this talk. So again, a phase shift, when the network gets big enough. And the series that we developed, this law of robustness is exactly a mathematical, theorem that justifies this empirical observation. So we say that scale is the law of robustness. So here is the theorem. On this slide, I'm going to describe the theorem informally, and then I will try to build up to why this theorem makes sense, and then give you the actual completely formal theorem. So everything that is on this slide, eventually, by the end of the presentation, is going to be formally defined, completely formal. Okay. So let us, for now, fix a reasonable function class. Again, I need to tell you what is reasonable, but reasonable is really reasonable. It's like basically anything which is not crazy. With P parameters, so for example, even just for a parameter to be meaningful, of course, you need to be reasonable. Like you can encode, RP and R are in bijection. So of course, you need some reasonableness there already. And what is reasonable? Well, maybe a deep neural network with polynomial size parameters, that's absolutely reasonable to me. Kolmogorov-Arnold type networks, that's not reasonable. Okay, just to give you an idea of what I'm talking about. Now, let me sample n data points from a truly high dimensional distribution. Again, I will perfectly define what is truly high dimensional, but for now, think that really you're exploiting all the dimensions. Okay, so maybe, you know, a mixture of Gaussian. This is something which is truly high dimensional. ImageNet is definitely truly high dimensional, although what is a dimension is kind of subtle. And when I say sample n data points from a truly high dimensional, it means, you know, you have pair input output, the xi and the yi. The xi's are from this truly high dimensional distribution. The yi's, they can be anything. You know, you have any target distribution, whatever, a small neural network, whatever you want. And now let's add some label noise. Okay, we want to add some label noise to make it complicated enough for what the task of fitting this data distribution. Then the theorem goes like this. If you want to memorize this data set, and the definition of memorization to me is really to optimize the training error below the label noise level. Okay, so you kind of overfit to the noise. You really memorize even the noise. Okay, so you're not in the early stopping regime. This is what I was trying to allude to on the slide with the benign overfitting. So you really memorize, you really overfit, which is what people do in practice. You know, they get to zero training error. And if you want to do so robustly, and what is my definition of being robust? I just mean it that the mapping, you know, that the neural network is learning is a Lipschitz map. Okay, it's just a smooth map, meaning that if I move by epsilon my inputs, then the output should move by epsilon. That's all. Then, if you want to both memorize and do it robustly, what you must necessarily, there is no other way around it, have dramatic overparametrization. Namely, your number of parameters should be larger not than n, which is what you need to just memorize, but n times d. So the ambient dimension of this truly high dimensional signal. Okay, so you really need much bigger network if you want to learn to memorize robustly. Okay, so this is the law of robustness, and in fact there is an entire trade-off curve between number of parameters and the Lipschitz constant that you can get, which I'm going to get to. But before I move to the more formal part of the presentation, I would like to revisit the examples and the scales that we talked about on the first slide in light of this theorem. Let's see what this gives us. So let's see what's some tentative implication on real data. So let's start with MNIST. So MNIST, it was 60K, so 6 times 10 to the 4. So let's round it up to roughly 10 to the 5. I'm only going to keep order of magnitude in this slide. So you have roughly 10 to the 5 data points. And again, it was 28 by 28, so it's roughly 10 to the 3 dimensional, at least 9. And the Madry et al. Experiment, they show a transition in the robust accuracy at roughly, a number of parameters, which is 10 to the 6. So first caveat, there will be several caveats, as in any application of a mathematical theorem to a real life situation, there are caveats, and we need to really address them and think about them deeply. So the first one is that here the notion of robustness that Madry et al. Measure is not the same as the one in the law of robustness. The law of robustness is about the Lipschitz constant. Madry et al., they were talking about robust generalization. So the two are related, but how related, it's not completely clear. But let's, don't worry too much about it. So if I take the law, like readily, it would tell me that I need a number of parameters, which is n times d, so roughly 10 to the 8. But, Madry et al. Is telling me that 10 to the 6 is enough. So this seems to contradict the law of robustness. 10 to the 6 is much lower than 10 to the 5 and 10 to the 3. But of course, it's because MNIST is not truly 10 to the 3 dimensional. The true dimension of the MNIST dataset, that's a very hard question. And in fact, there was a talk earlier in this conference, saying that maybe the true dimension is 3, or, it's certainly small. I think a reasonable effective dimension is in the order of 10 to the 1. Okay, so is it 5? Is it 15? Is it 20? I don't know exactly, but it's certainly not 10 to the 3. And of course, if you take 10 to the 1, then you get perfect match between the law of robustness and the experiment. The law of robustness would exactly tell you that you can start to expect to be robust on MNIST when you get to 10 to the 6. Okay, 10 to the 5 times 10 to the 1. So, this is a pretty good match. Now, let me bring the second caveat, which is, the law of robustness needs to have noisy labels. And this is necessary mathematically, because if there is just no noise, then of course, you cannot prove any lower bound on a function class, because, if the true target is some function, well, this function could just be in your function class, and that's it. There's nothing you can do. So of course, you need, in theory, to have some noise for something like a law of robustness to occur. But really, we would like to think of this theory noise level as kind of measuring the difficult part of the learning, the part where you really would need a very, very complicated algorithm to kind of fit this part of the training data. So here, to really go beyond the label noise, we would need to talk about inductive bias and algorithmic regularization, which I won't do, and I don't know how to do it, and I will maybe come back to it in the open problem at the end. But roughly for MNIST, we would like to think of this noise as a couple of percent, and depending on the exact number where you put, okay, when is it that you reach below the noise level? If I go on this picture, whether it's at capacity scale 4 or capacity scale 8 or 16 that you reach, these are different order of magnitudes for the number of parameters. So it's really important to answer this type of question. Okay. But now, more interestingly, MNIST, Madrid did the experiment, they saw a phase shift at 10 to the 6. But now on ImageNet, we don't have robust models currently. So let's run the same experiment, sort experiment on ImageNet. So ImageNet is 10 to the 7 data points. It lives in dimension 10 to the 5. So maybe, if I take what happened in MNIST, where we went from 10 to the 3 to 10 to the 1 for the effective dimension, let's say you have the same linear ratio between the observed dimension and the effective dimension for image data set, maybe, I don't know. Then, this 10 to the 5 would become 10 to the 3. So the effective dimension would be 10 to the 3. So the law of robustness predicts at least 10 to the 10 parameters are needed. So that means that maybe we are not robust on images just because we're training too small models. Our models currently, they have only roughly 10 to the 9 parameters on ImageNet. We're talking about 100 million, 500 million maybe parameters. That's the state of the art on ImageNet. But really what we're saying is, no, actually you need, 10 billion. In fact, maybe even 10 to the 11, because this effective dimension of 10 to the 3 is maybe a bit conservative because the ImageNet is more complicated. There is 1,000 classes, etc. So maybe it's 10 to the 11. Okay, so we're already talking about maybe you need GPT-3 scale of neural network if you want to be robust on ImageNet. This is actually the prediction that the law of robustness makes. Okay, and I don't know if it's true. This needs to be checked. Okay, so now let's do some mathematics. Okay, so I need to define all those terms, what they mean, and why do I use them. So the first one is a dramatic overparametrization. Why do I call n times d dramatic overparametrization? Well, it's because memorizing n data points, it should require, this is really about satisfying n equations, so n parameters should be enough. Okay, there are like infinitely many ways to formalize this sentence, like really, really many. In the context of neural networks, there is this nice theorem of Eric Baum from 1988, which says that the two-layer neural network with a threshold activation function only needs k, where k is the number of neurons. Okay, so number of neurons for a two-layer net and number of parameters are related by a factor d. So you only need n over d neurons, meaning only n parameters to memorize binary labels. In fact, these two papers, but these papers do much more than this, but in particular, they also show that the same statement is true with a rectified linear unit activation for real labels instead of just binary labels. So, exactly the same, you only need n over d neurons. In fact, we even prove that even NTK can do it. So you don't even need to be very delicate and very subtle. You can just take random neurons and, slightly perturb them, and this will, do the job. Okay. So only n parameters is enough to memorize. Now, what about the smoothness of these constructions? Well, all these constructions, it's pretty easy to calculate that they are actually very non-Lipschitz. Okay, so they are very sensitive to the input. And in fact, you can show that they are all square root d Lipschitz, or if, in fact, even worse, in the case of well-dispersed data. What I mean by well-dispersed data is let's normalize things and let's assume that, for example, your xi are IID on the sphere. Okay, they are IID unit norm vectors. But notice that IID unit norm vectors, of course, you can memorize it with just a constant Lipschitz. Okay, you don't need to have a Lipschitz constant that blows up with the dimension. We assume always that the number of data points is polynomial in D, and this sentence is equivalent to this picture. So if you have polynomially many points in high dimension, then all those points are very, very isolated from each other. So if you have like I don't know, d to the 5 points, then certainly around each data point there is a ball of radius 1 over 10, let's say. So a big, a chunky ball, like a ball of radius 1 over 10, which is just completely empty. There is no other data points. So if I wanted to fit my data, I could just add a bunch of bump function. I can do a little bump function around this data point. So it goes, from whatever value I want at the center, I don't know, +1, -1, whatever you want, and it decreases to 0 in distance 1/10. So this bump function sees only one data point. All the other data points, it says 0. So I can just add a bunch of them, and I will perfectly memorize whatever I want. And this is 10 Lipschitz. The only thing is that it moves from a value 1 to a value 0 in distance 1/10, or maybe it's 20 Lipschitz because there is a little bit of curvature. It doesn't matter. So this picture, you can imagine, it's very easy to realize it with only n neurons, right? I just need a constant number of neurons per data point. So in terms of number of parameters, this is exactly n times d. So with n times d parameter, I can trivially memorize my data and do it smoothly. Okay, so just to summarize the last two slides, or what I said on this slide, we have two options. Either you take a small model, okay, so this Eric Baum construction or NTK or whatever you want, which has optimal number of parameters of order n, but this will be very non-robust. The Lipschitz constant will be square root of the dimension. Or you can have very large model where the number of parameters is n times d, and this will be very robust. Okay, so you get more parameters, but what you win from more parameters is being more robust. And the question, obviously from this slide and from this construction is this trade-off real? You really cannot do, better, like in terms of size of the model versus robustness. And in fact, the general relation is square root of nd over p. Okay, that's very easy to figure out from this picture. You can just do this picture by projecting it into a lower dimensional space, and you will get exactly this relation. So can we do better than that? And the law of robustness exactly says that this is tight. And the surprise is that not only is this tight when you try to do construction with two-layer neural network, it's tight no matter what function class you use. It's completely general. Now let me tell you, the formal theorem, where I will define everything precisely. So let f be a class of function from Rd to R, and let xi, yi be an IID data set of input-output pairs in Rd times -1, 1. Okay, so your target function is just bounded. And let's make a few assumptions. The first one is, remember that the function class is reasonable. What does it mean? It means that f admits a J Lipschitz parametrization by p real parameters. So we have p real valued parameters, and this parametrization is Lipschitz. Okay, meaning that if I modify one parameter by a little bit, then the function itself that is computed changes only a little bit. Maybe you can, whatever, you can do L infinity norm, between functions, or whatever norm you want, doesn't really matter. And moreover, those parameters are not too big. They are of size at most b. Okay, and all that will matter is J and B is the crucial part, is that J and B only enter logarithmically in the bound, meaning that I basically need to assume nothing except that they are polynomials. Okay. Now, the next thing is, I told you that the distribution of the covariates needs to be truly high dimensional. So what does it mean for me? It means that the distribution of the xi satisfies isoperimetry. Or in fact, I don't even need that. I only need to have a mixture of distributions that satisfy isoperimetry, and I can have as many as little o of n over log n components. So I can have a huge number of components. If I could have as many as n components, this would be a non-assumption, basically. Here, I cannot get all the way up to n components. I can have only n over log n. And what I mean by satisfy isoperimetry, technically what I mean is that Lipschitz functions under mu, they concentrate around their average, just like you would get a concentration for uniform distribution over a sphere. Okay, so this is the assumption of isoperimetry. And again, the fact that you can have a mixture of those things really means that I think it's a very practical assumption. Which again, the point of this assumption is really to make D have a meaning. Okay, D needs to have a meaning, because if you make no assumption, then all your data could line on a line, and then D has no meaning. And finally, I need label noise. So the expected conditional variance of the output is strictly positive. So the variance of y given x in expectation over x needs to be strictly positive. And then the theorem goes like this: with high probability over the sampling of the data, for any function f, if you fit, if you memorize your data, meaning your training error is below sigma squared by some gap epsilon. So again, I think it's better for now to think about sigma and epsilon as some constant. Then the Lipschitz constant needs to be larger than square root nd over p. And you just have this epsilon squared, which corresponds to this, doesn't really matter, and you have log of bj. Okay, so really, up to this epsilon squared, there shouldn't be a tilde. These are all the things that matters, and there's just a constant. So, if b and j are polynomial in n, then this log disappears basically, and this epsilon squared, again, think about it as a constant. So it really tells you the exact trade-off between the Lipschitz constant and the number of parameters, the number of training points, and the dimension. And this is tight because I just told you that there is a construction that can also verify it. Okay, so this is the formal theorem. Let me conclude with some remarks and open problems. So first of all, the term log b is necessary. You need, to have, of course, the term, I guess the term log bj is necessary. And why? How do you see it's necessary? Well, with 3 layers, with 2 hidden layers, you can use Kolmogorov-Arnold with b, which is exponential in n, and this will break the law. Basically, you can fit anything with 3 layers and exponential size weights. You can more than fit anything. You can approximate any function. So you can, in particular, approximate, whatever is a smooth interpolation using only d neurons. Okay. Now, I told you it's necessary. Actually, it might not be necessary for the case of 2 layers. And this is what we conjectured in the previous paper with Yuan-Julie and Dheeraj Nagaraj. We conjectured this law of robustness for 2-layer neural network, but without the log p. And this is still open. Okay, we still don't know how to prove it, but I think it's now of pure mass interest because we know that it's necessary as soon as you go to 2 hidden layers. And also, it's very hard. I mean, the reason why we couldn't prove it a year ago, I think, it's because it's hard. It's because K is the number of neurons for a 2-layer neural network. It's basically like the rank of a certain tensor. So this was really about proving lower bounds for rank, which is difficult. Another point that I want to bring to your attention is that, this is completely universal. This applies to any function class. So any, transformers, ResNet, whatever you want, the law is just there. It's true. But in fact, sometimes for certain function classes, it could be that even stronger laws exist. So in our previous paper in BLN, we proved that for 2-layer neural network with quadratic activation function, which basically correspond to computing a quadratic map, you have a stronger law, namely square root of n over k times another factor square root d over k. So we showed that for low rank quadratic network, in fact, it's even worse. Like you cannot even match the law of robustness. And finally, this 5th point is very important, very subtle. I know everybody would like to have a law of robustness, which is not about the Lipschitz constant, but something more delicate, like an expected Lipschitz constant or something average. But I want to bring your attention to the fact that these things are very delicate and subtle. So you would like to have a law of robustness where you use a different measure of robustness, a different measure of smoothness, but not all measure of smoothness admit a trade-off. So for Sobolev norms, like the expected norm of the gradient squared, for example, is just trivially false. Like it's very easy to see that the Baum construction will have, a Sobolev norm which is exponentially small. So there is no way to hope for a trade-off. And for standard generalization measure, like the Baron norm, for example, for a 2-layer neural net, then in our paper with Ronan Eldan, Yintat Li, and Dan Mikulincer, we in fact showed that you can be optimal both in terms of Baron norm and in terms of number of neurons. So this is a measure of smoothness where you just don't have a trade-off. Okay. So conclusion, the law of robustness, I think, is real. You actually need to overparametrize if you want to be both smooth and have low training error, unless maybe you use exponentially large weights, but okay. Mathematically, the unrestricted law for 1 hidden layer is still interesting. Also, I didn't mention how the depth enters those bounds. So because J, the Lipschitz parametrization, can be exponential in the depth of a neural network, then the depth enters the bound like this. It's really depth times number of parameters. But I think this is actually, extraneous. You can probably remove this capital D. I have some ideas, but I don't know how to do it. A much more ambitious goal would be to prove a law of robustness with a more realistic noise assumption. This seems very hard. Other norms to measure robustness, other notions of robustness, this is very delicate, very difficult. Stronger laws, what can you do? And of course, point 6, I think there is a lot of room for more empirical studies to confirm this law. Okay, I will conclude here. Thanks.